wrap up the session. Okay, so why don't we go ahead and get started. I'd like to call the first speaker, who is Jen Boyko from Haverford College. She actually performed her research here at Ohio Wesleyan this summer with my colleague Scott Linder. And the title of her talk is Interference for the Regression Coefficient in a Bivariate Normal Model when Data has been subjected to censoring. And I'm sure she can explain that much better than I possibly could. So let me get this set up for Jen here.
Inference, not interference.
Oh, I'm sorry. Inference. See?
Don't need to interfere.
Like I told you. Yeah. Okay, thank you.
Good morning, everybody. I'm Jen Boyko, and I've been working with Dr. Linder this summer on a project entitled Inference for the Regression Coefficient when Data has been subjected to censoring. Censoring is actually very common in an industrial setting. Say you are conducting a clinical trial, and over time some of your patients drop out of the trial. You don't know their results, so that data has been censored to you. There are two types of censoring, conveniently called type 1 and type 2 censoring. With type 1 censoring, you stop the experiment after a specified amount of time has passed, and therefore the number of observations is random. With type 2 censoring, you stop the experiment after a specified number of observations, and therefore the duration of the experiment is random. Our research deals with type 2 censoring, and to give a better example, say you begin an experiment with N monkeys. You feed each of them a high-fat diet, and you wait for some of them to die. You record X, which is the time of death, and Y, which is the amount of plaque in the aorta. You stop the experiment after P of the monkeys have died. The N minus P observations, or all of the observations after the P observation, have been censored to you. However, we do know something about them. We know that their X value has to be larger than the maximum X value of the recorded data. This is an example of single censoring. We also studied another censoring scheme called symmetric censoring, in which the middle P observations are recorded, and the N minus P over 2 from either end are censored. Our main research question deals with how X and Y are related. And to do this, we look at linear regression. X and Y are related by the equation y equals alpha plus beta x plus epsilon, where epsilon is the error and is normally distributed. The regression coefficient beta is dependent on the correlation coefficient between x and y. Independence of x and y implies that beta equals 0. Say from your data, you calculate your experimental beta, which we'll call beta hat, and it turns out to be 0.2. Now, is this sufficiently far enough away from 0 to reject the hypothesis that beta is 0? Well, you don't know without knowing something about the sampling distribution. The sampling distribution is the distribution of all beta hats when beta is assumed to be 0. So say you find beta at 0.2, and the sampling distribution looks like this. Now you should have a better idea of whether or not you should reject the null hypothesis when your experimental beta is 0.2. One of the ways to estimate beta is with the maximum likelihood estimator. This is the estimator that maximizes the likelihood function and is also known as the least squares estimator. This estimator's sampling distribution is mathematically intractable and must be approximated. This is an example of the distribution of beta hats when n is 30, p is 12, and beta is 0.9. As you can see, the curve isn't smooth and no exact distribution can be fit. However, you can fit an approximate distribution, which is this line here. Earlier in the summer, we were trying to fit approximate distributions to the sampling distribution. However, our research digressed into these two objectives. The first is to develop a method for approximating the power of a test for independence. And the second is to consider a quick estimator in lieu of the NLE. The power of a test is the probability of rejecting a false hypothesis. Say I told you that I weigh 900 pounds. The probability of you rejecting this hypothesis is probably pretty high because you've looked at me and you've taken in data about how much you think I weigh. Now say I told you that I weigh 120 pounds. You're probably less likely to believe this and less likely to reject the false hypothesis, so the power of the test is low. This is the equation for the power of the test. There are three sources of variability: beta hat, SSXX, and SSE. Because of these sources of variability, this quantity needs to be approximated using simulation. We propose an alternative approximation by replacing the simulated values of x with their tabulated average values, which replaces SSXX with SSUU. Doing this, we eliminate a source of variability, and then we can approximate the power without simulation. Here you have the replaced quantity where SSUU replaces SSXX. This quantity has approximately a non-centralized t-distribution with parameter delta. This quantity can be calculated using many software packages and isn't that difficult to calculate. Delta is defined as with this equation here, and this is also free of simulation. Here we have a graph comparing the exact power, which is the solid line here, and the approximate power, which is the dotted line. As you can see, the approximate power has a very smooth curve, and that is because it is free of simulation and therefore variability. It is also a conservative estimate of power, especially when beta is between about 0.3 and 0.9, because it is lower than the exact power. This particular case is when n is 20 and p is 12. By doing this for many values of n and p, we can look at the power of the test and therefore choose a sample size depending on what we want our power to be. Here we have a table with two values of n and p. You can see again that the approximate power tends to be lower than the simulated power. And the relative error is between about 1% and 20%. This table shows the minimum value of p needed to achieve a desired power. So say that you think it's significant when beta equals 0.6 to reject the hypothesis with a power of 0.2. If you start with 10 samples, you need 8 to achieve this power. If you start with 20, then you need 11, and if you start with 30, you need 12. This allows experimentalists to design their experiments based on the desired power. The second thing that we studied was the Barton and Cayley estimator. This estimator uses the average of the first k values of the ordered pairs and the last k values to calculate beta star. Beta star is a function of k. So a natural question to ask is, what is the optimal value of k that approximates the Barton and Cayley estimator closely to the MLE? This is a full sample when n is 100. All of these data points would be used to calculate the MLE. The Barton and Cayley example, on the other hand, uses only the first 10 data points and the last 10 data points. And it averages those two and computes the slope between the two averaged points. Now you might think that more data equals a better approximation. However, when k is very small, you have a more stable estimation of the slope. So the optimal value of k is the value of k that rectifies these two theories. Here's a comparison for n is 20 and p is 12 of comparison of the MLE and the Barton and Cayley estimator for all values of k. We compare them using the efficiency, which is the variance of beta hat over the variance of beta star. The closer the efficiency is to 1, the closer the Barton and Cayley estimator is to the MLE. We look for the maximum value of efficiency and the value of k that it occurs at. For symmetric censoring, k is 4, and that's the optimal value of k that maximizes the efficiency. Here we have a table of all of the optimal values of k for all of the cases of n and p that we looked at. For single censoring, we found that the optimal value of k occurs between 1/4 and 1/3 of p, and efficiency tended to range from 70 to 80%. For symmetric censoring, we found that the optimal value of k ranged from between 1/4 and 2/5 of p, with efficiency ranging between 80 and 85%. So how do we apply this research? Say I'm doing the monkey experiment, and I want to reject beta, the null hypothesis when beta is really 0.7. And I want that to happen about 30% of the time. Well, I reference the chart. Beta is 0.7 and power is 0.3. Now, I could start with 10 monkeys and wait for 8 of them to die, which could be a fairly long experiment. Or I could start with 20 and wait for a lower percentage of them, 11, to die. But maybe monkeys are expensive and I can't afford to do that. So with this information, a researcher can decide what the ideal situation for them is with their situation. I'd like to thank NSF and the REU program for funding this research, and Ohio Wesleyan University for hosting this program and this symposium. And of course, I'd like to thank Dr. Linder, without whose guidance I wouldn't have the first clue where to go with this research. And of course, thank you for being such a receptive audience.
Thank you, Jen. Any questions for our speaker?
Yes.
I noticed that on the chart, like the last chart that you had, that sometimes your, sometimes your values, oh, those aren't negative signs, now I see.
Oh, I completely forgot to
What does it
explain
mean
that.
to not to have a value?
What it means that for that value of n, you can't have p large enough that you can reject the test with a power that high under those conditions.
Any other questions? Yeah, Sean?
This might not be a good question, but so there's two kinds of things you're looking at. There's the graph where it's stopped after a certain amount of monkeys die or something, and then there's the graph where there's the big hole in the middle.
Right.
How does that relate to like a real experiment? What would that look like?
What that means is, I mean, I didn't demonstrate it for the censored case, but say you had a full sample, the MLE would use that whole sample. I mean, you have the data points for all 100. Barton and Paley would only use the first, for example, 10, and the last 10 to approximate data. They still have all the data. They're just choosing not to use all of it to approximate the regression coefficient.
And you're saying that you can end up with a better or more reliable result by just choosing a certain fraction than total concrete normal logic. You would think to use all the data is better, but you're saying you could actually do better with either extreme.
Yep.
Okay, if there's no further questions, let's thank our speaker again.